Question number 6. Dodecane is a hydrocarbon found in the naphtha fraction of crude oil. Dodecane can be used as starting material to produce a wide variety of useful products. The schema in figure 2 shows how one product, polymer Y, can be produced from dodecane. Okay, so what I've got is I've got dodecane making these two chemicals here, and then I've got an unknown one here, but this C4H8, lots of these, n number of them, not sure how many, n just represents a number of them are joining together in this polymer. So what actually happens is C4H8 has got the general formula CnH2n, because the 4 doubled makes an N. It's got a double bond in it, and so is this as well. It's got a double bond, and the double bond breaks, and as the double bond between those two carbons breaks, it allows an extra bond either side to form, and it forms single bonds, a long chain, a long saturated chain. So I've got C4H8 here, I've got an alkene with a double bond that then breaks to make a chain, a polymer chain of single bonds. Name the homologous series that both C2H4 and C4H8 belong to. Well, general formula CnH2n, that number there, the number of carbons, the 2 gets doubled to a 4 and the 4 gets doubled to an 8. Then the functional group, it's going to be an alkene. It's got double bonds in it, so it's an alkene. Now, what's a functional group isomer? So, a structural isomer is where the molecular formula stays the same, C4H8 stays the same, the molecular formula stays the same, but the structural formula changes. That's a structural formula. So C4H8 has changed its structure, retained its molecular formula, but changed its structural formula. So a structural isomer does that, and there's 3 kinds. Number 1, a chain isomer. That's a structural isomer, a chain isomer. Number 2 is a positional isomer, and number 3 is a functional group isomer. So a functional group isomer is a structural isomer. It's one of the 3 kinds. Let's just remind ourselves. A chain isomer might be where I'll take a chain of 4 and make a chain of 3 with a branch. A position isomer is where I might change the position of the functional group. So if that were but2-ene, it might become but1-ene. I change the position of the double bond from a 2 to a 1, change its position in the chain, but it's not, it's a functional group isomer. That means I've got to change the functional group. What identifies it? Well, what identifies an alkene is the double bond. In other words, I've got to retain the molecular formula C4H8, but I've somehow got to get rid of the double bond. So how on earth can I have C4H8 and get rid of the double bond and make single bonds? Well, the only way that I can do that is to make it cyclic. I can put it in a circle. Look, all the carbons have 4 bonds, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, fine, and I've got 8 H's and 4 carbons. I've maintained the structural formula C4H8 by making it cyclic in structure. Identify compound X. Well, I've got to work out what's left over essentially. C12, I've got 12 carbons on that side, I've got 2 there and 4 there. 2 and 4 is 6, and I've got 12 on this side. So I've got 6 missing carbons. That must be C6. That's H26, and I've got 4 and I've got 8. 4 and 8 is 12. So I've got 12 H's on this side. I started off with 26. I've got 14 in there, so it's C6H14. Name the polymer Y. Well, what's happened with polymer Y is this molecule here, before it's made 2 bonds either side, has had a double bond. So this molecule inside the brackets has had a double bond between the 2 carbons, and then lots of these molecules have joined together, the double bond split, and a bond's gone out either side to make a whole long polymer. So it's this chemical here has been this one, but instead of having a bond either side, it's had a double bond in the middle. The longest carbon chain, if you trace it round, it doesn't have to be in a straight line, it just needs to be in some kind of line connected together. 1, 2, 3, 4. So it's had 4 carbons. It's some kind of bute, and it's had a double bond. It's bute with a double bond, butene, and the double bond is between carbons number 1, 2 and 3, 4, 2 and 3. So it's on carbon number 1, 2, but-2-ene, and it's a polymer. So we put the word poly but-2-ene. So poly-but-2-ene. So we, for a name of a polymer, we write down what it's come from and we put the word poly in front. It's poly-but-2-ene. That's what it's called. Okay, an example of thermal cracking. So thermal cracking is where you break up a long chain. So I might heat this polymer up and break it up. In other words, reverse the reaction. And when I do so, I tend to make compounds with double bonds in them. So thermal cracking is where I break a long chain up into a series of short chain alkenes. I need a high temperature, and I need high pressure as well. You just got to learn that. Reaction 2 is exothermic. So this reaction here is exothermic. It gives out heat. When I say it's exothermic, it gives out heat when I turn the left-hand reactants into the right-hand products. It gives out heat from left to right. So as it goes left to right, it's exothermic, going to give out heat. When it goes right to left, it's endothermic. It's going to take in heat. Exothermic that way, endothermic that way. Exothermic. A typical compromised temperature of 200 degrees C is used. Okay, explain why the effect of change of temperature on both the position of equilibrium and the rate of reaction justify why a compromised temperature is needed. 6 marks. That's hard, that, because we haven't got any of the question broken down. We've got to work out where the 6 marks are. So first of all, I would say the reaction is exothermic, gives out heat. Gives out heat in the forward direction. So in other words, when these reactants go to these products, gives out heat in the forward direction. And Le Chatelier's principle then says that what will happen is the equilibrium position will shift to oppose any increase in temperature. So Le Chatelier's principle says that the equilibrium position, that's for a reversible reaction like that, will shift to oppose the change. So what will happen, the effect of a change of temperature? As I increase the temperature, what's going to happen? So I put the temperature up. What's going to happen to this reaction? Well, Le Chatelier's principle says it will shift to oppose any increase in temperature. So let's look back at this reaction here. When it goes from here to here in the forward direction, it gives out heat. If I provide more heat, I make it hot. If it's going that way and making heat, and I provide more heat, what actually happens is it shifts to lower the temperature. If I'm increasing the temperature, its position will shift to try and oppose that change and lower the temperature. Well, left to right, it's making heat. Right to left, it will take in heat. So if I'm providing heat to the system, the way that it can shift and oppose that change, in other words, lower the heat, reduce the heat, make it cooler, is by going right to left. Because left to right, it makes even more heat. And providing heat, it doesn't want to make more, it wants to remove that heat and oppose the change. It will shift right to left. So Le Chatelier's principle says that it's going to shift, the position of equilibrium is going to shift to oppose any increase in temperature, i.e. lower the temperature, and the way it can do that is going right to left. Next one. So a higher level will reduce the yield. So the yield means how much of this is made. Well, if it's going that way and it's exothermic and making heat, and I provide more heat, it will go right to left now to oppose that change and try and lower the temperature. And if it goes right to left, instead of making more of this on the right, it's actually making more of the products that we started with. It's going to lower the yield of the product. A higher temperature provides more molecules have a higher energy. So more molecules have the activation energy or above. That's what happens. The activation energy is the minimum amount of energy for particles to collide successfully. So more particles now have the activation energy and have more successful collisions. and so the rate of reaction will increase. So I've got two conflicting things happening here. I've got Le Chatelier's principle saying that if you increase the temperature, the position of equilibrium will shift to the left and reduce the yield. However, a high temperature is needed because at higher temperature more molecules have the activation energy, so you get more successful collisions and the rate of the reaction increases. And that's why I've got two opposing things happening. At a higher temperature I'm getting a lower yield because the equilibrium position is shifting to the left, but at a higher temperature I'm increasing the rate. So these two are directly in competition with each other. So what actually happens in industry, you use something called a compromise temperature, a temperature that's somewhere in the middle, so that the equilibrium isn't shifted completely to the left and you end up with a low yield, but you have a high enough temperature. You have a high enough temperature so that the rate you've got a reasonable rate, but you've got a not too high a temperature so that the equilibrium shifts too far to the left.